Welcome, students, and welcome to our next chapter. And today we're going to be talking a little bit about acids and bases and what those are and what those mean, um, and how to identify them. Mainly is what we're going to be dealing with today. And later on, we'll get into such things as you've heard, things like the pOH scale and what that means. And you guys maybe even in middle school did some experiments with what are called indicators, maybe like purple cabbage juice, and tested some different substances. We'll do some things like that in class and demonstrate those. But before we get there, we need to kind of define what an acid and a base is. So that's basically what we're going to do today, is figure out what are acids and bases. And there's really, over time, there's really three major definitions. One of those definitions is the one that we will spend the most of our time in, and I'll point that out in a minute. But let's start with one of the earliest definitions. So defining acids and bases, and this is not just a definition. Of course, you'll need to know this for the test purposes. But these are also the main ways that you identify, a acid or base, and that's big time what I'm going to have you do on the test, and want you to be able to know so that you can distinguish. Well, is this an acid or is this a base? One of the earliest ones was an Arrhenius acid, and named after the gentleman who was involved in kind of defining this and working this out. And these are substances which release hydrogen ions into an aqueous solution. You guys kind of are already familiar with an aqueous solution. Typically when we think of acids, we think of liquids. That's because they are. And so this would be a substance that gives off hydrogen ions. An acid, and really bases as well, are always ionically bonded. Okay, so in this case, hydrogen, even though it's a nonmetal, would be acting as the positive ion, or the metallic ion in a sense, because it's positive. And then it'll be bonded to some nonmetal that will be negative. And of course, when you put an ionic bond, something that's ionically bonded in, let's say water, okay, to make an aqueous solution, those ions separate. And so that's what it means when it's saying it releases a hydrogen ion into an aqueous solution. And a base, okay, an Arrhenius base is a substance that releases hydroxide ions. Earlier on, we learned about the polyatomic ion hydroxide. Now we're actually really getting to use it a lot because these are associated often with bases. Here you have the several different examples, and on the left side, as you're facing the screen, you'll notice those are all, that column there, those are all acids, okay, and Arrhenius acids as defined. And you'll notice what they all have, and kind of the easiest way to, in a sense, identify them, if you're wanting, how do I identify or know that it's going to release a hydrogen ion? Kind of the easiest way to identify it is you notice they all have hydrogens, and those hydrogens are out front. That's because in an ionic bond, the positive substance is always to the left, and the negative ion is always to the right, if you remember. Okay, so in the first one there, hydrochloric acid, you have HCl, and so hydrogen, it's capable of releasing that hydrogen ion. Obviously, if it didn't have a hydrogen ion, then it wouldn't be capable of releasing it. And then you have sulfuric acid, which is H2SO4, and then phosphoric acid there, which is H3PO4. And the easiest way to identify them is, hey, they all have H's, and those H's are out front. That tells me that's an acid. On the other hand, okay, on the right side, you have your bases, and you'll notice they all have hydroxide. Hydroxide is that OH there. And those are together. Okay, that H is not separate from that oxygen. They're bonded together, if you remember, in polyatomic ions. And so you have sodium hydroxide there. The first one, it has a hydroxide ion, and therefore, if I put it in a solution, that hydroxide ion is going to separate from the sodium ion, and therefore it would be defined as a base. Okay, next one, magnesium hydroxide. Again, it has hydroxide. Next one, aluminum hydroxide. Again, it has hydroxides. In this case, 3 of them. All of them have hydroxides. That's your indicator that this is a base in this case. Now, so far so good. If that's all there was to it, it'd be really easy to distinguish between an acid and a base. There you go. You're done. And to some extent, some of this we will use in class and on the test in terms of identifying an acid or a base. Some of them will be this simple. You see a hydroxide, oh, that's a base. Or you see a hydrogen out front, oh, that's an acid. But, as scientists sometimes like to do, things get a little more complicated than that because there are some, as time went on, and we found that there were some things that had basic or acidic properties that didn't fit into the current definition, so we needed to expand that definition. And so we get to our next set of definitions, and this is the one that we will use the most, at least for our purposes, and that is the Bronsted-Lowry definition. And this is inclusive of everything in the Arrhenius definitions, but it's going to add a little bit more. And Bronsted-Lowry acids are substances which donate protons. Now, really this definition doesn't change from our previous definition of an acid, and here's why. If we were to go back, so let's take a look at this real quickly. And we look at HCl. Okay, according to the old definition, hydrochloric acid is a substance that's going to release a hydrogen ion. And we know that because there's a hydrogen out front there. Okay, look at the new definition here. Is a substance that donates protons. All right, well, let's ask ourselves, what is a hydrogen ion? Okay, well, a hydrogen atom is made up of one proton and one electron. So if it becomes an ion, in order for hydrogen to become an ion, it has to lose that electron. And so what's left in a hydrogen ion? Just a proton. So when we're saying a substance that donates protons, what we're saying is it's a substance that donates a hydrogen ion. So the wording is basically the same, it's just saying it two different ways. So again, when it comes to acids, I'm still looking for, does it have a hydrogen? And I just have to understand that hydrogen is an ion, and that ion is simply a proton. So when we talk about donating protons or hydrogen ions, it's the same thing. Okay? So the definition really for acids hasn't changed. What has changed is this. Bronsted-Lowry bases are substances which accept protons. Okay, well, this still includes hydroxides, can be counted in there, but now we're going to expand our definition a little bit, because what can accept a proton? Well, let's think about it. What is true about a proton? Okay, well, it's in the nucleus, we know that. But what else? What other feature is kind of distinct about a proton? That's right, it's positive. Okay, it's a positive charge. So what would have to be true about a substance that would accept a proton? It would have to be negative. Okay, so what we're looking for now are substances that are negative in order to be able to attract or accept a proton, okay, or a hydrogen ion. Remember, anytime we're talking about accepting or donating protons, we're talking about a hydrogen ion. It's not just a random floating proton out there. Okay, so this is a hydrogen ion. These are substances that accept protons. So when we're talking about a Bronsted-Lowry base, we're talking about a base, something that's negative. And we're going to get into this here in just a minute and show you how this works. Okay, so understand that's what's expanded about our definition. So now bases are not only things that can be classified as substances that have hydroxide, but now we're going to go a step further, and we're going to say they're also substances that would be negative. So if you had a negative ion, well, that could accept a hydrogen ion, that could accept a proton, and therefore that also could be defined as a base. So our definition of bases has expanded a little bit. All right, the last definitions, two definitions, are what we call the Lewis definitions. And these deal more with, instead of protons or donated hydrogen ions, these are more dealing with electrons. And these two definitions I'm going to put up here real quickly. I'm not as concerned with them right now. We may touch on them a little bit later. and kind of, how do they play into and how do they differ, or what do they add to our definitions. Right at the moment, though, I'm not going to fixate on them other than you writing down and making sure you get the definition. Because I do want to go back to the Bronsted-Lowry acids and bases and kind of touch on a concept we call conjugate acids and conjugate bases. So before we go anywhere else with the Lewis acids, other than you getting those definitions, we want to fixate on the Bronsted-Lowry kind of definition and wrap our minds around that. What does that mean? What would it look like? Okay, so conjugate acids and conjugate bases. Before we actually get to conjugates, the first thing we need is two terms here, protonation and deprotonation. Protonation is the addition of a hydrogen ion or a single proton to a substance. Okay, so this would be if we were talking about a Bronsted-Lowry base being able to receive a hydrogen ion or receive a proton. That process of adding that hydrogen ion or that proton is what we call protonation. Okay, accepting one. Deprotonation is taking away a hydrogen ion or a proton from a substance, whatever that particular substance. So that would be removing a hydrogen ion. So remember those two terms, because we're going to use those occasionally in this chapter, and it would be useful if you knew what they meant. Okay, protonation is adding one, deprotonation is removing a hydrogen ion. Okay, so let's see how this works. Conjugates. Okay, conjugate acids and bases is basically this. Things that kind of work together. So first of all, let's start with this. If this was your example, HCl there, is that an acid or a base based on the definitions that we've had so far? If you were asked to identify that, what would that be? Okay, the correct answer is that would be an acid. How do we know that? Okay, well, we see that hydrogen out front, so from the Arrhenius definition, that hydrogen tells us that's it has a hydrogen ion that it can donate. From the Bronsted-Lowry definition, that's a proton that can be given off as well, and so it's an acid. All right, well, if it's an acid, then I need to find the conjugate base. Okay, if I'm starting with an acid, then what I won't need to find is its conjugate base. In other words, what base goes along with it. And by base, we're talking about what Bronsted-Lowry base would be connected with this acid. And the way we do that is we would go, if you're starting with an acid, then you're going to go, you already have your ion, so you're going to go through the process of deprotonation. If you were starting with a base, then you would need to go through the process of protonation, adding a hydrogen ion. Okay, and we'll look at that in a second here. So in this case, since I'm starting with an acid, I need to get rid of that hydrogen ion, or at least one of them. If there was more than one, then I would only need to get rid of one, okay, at a time. But in this case, there is only one. So I'm going to remove it, okay? So my conjugate base for this particular acid would be Cl negative, okay, which makes sense because we said that, okay, if you have a negative substance there, like this one here, it's capable of adding a proton or accepting a proton, which fits our definition, okay, for a Bronsted-Lowry base. So if you need to kind of go back to that definition and look, that fits very well. So that would be our conjugate base. Well, what about, okay, if you had, let's do another example here. What if you had, let's say, this nitrate here, NO3 negative? Is that an acid or a base? Well, it doesn't have a hydrogen ion or a proton out front to donate, and it's negative, so that means it can accept a proton. So therefore, by the definition, it must be a base. Okay, well, because it's a base, what can I do to it to find its conjugate? Well, if my starting point is a base, then its conjugate would be an acid. Okay, in other words, that's the relationship between there. So what would the conjugate acid be? What would I have to do to it? I would have to add, okay, a proton. It would have to go through the process of protonation to it. And if I did that, then I would end up with this acid, nitric acid, okay, HNO3. And I'm done. So really, if you want to boil it down, when you're asked to find conjugates, if you start with an acid, you're going to remove that proton, and you'll end up with a negative ion. Okay? If you start with a base, which, and the way you would know that is it would be a negative ion, and you're asked to find you would find the acid, and the way you would do that is by adding a hydrogen ion or proton to it. And that is it.